So we were discussing about the statement of the three laws that we understood last time: the law of inertia, the law of force, net force as the rate of change of momentum, and the action-reaction principle, which was the third law. And through that, we understood some examples of how to apply second law by calculating the net force acting on a body as the vector sum, etc. And to that end, I gave you a couple of a few problems to work out from the worksheet. So let's begin by understanding some of those questions. So we will do the discussion of the worksheet 1 first of all. Right, so if you can just turn to the worksheet. So I'd like to start with the discussion of question number 2. Yeah, so now whatever doubts you have, you can keep sending me, I will discuss. Okay. So I'll start with the second question. The first question, you have a doubt, I think you'll be able to solve after you go through the second question solution that I'm doing over here. So it says that a force F naught causes an acceleration of 5 meters per second square when acted on upon an object. Okay. So basically that means that if you have an object on a surface like this. Okay, we will discuss all these questions. I'll come to the 5th, 7th, 11th and 12th also. But let's start with the second one. So if we have an object of mass m and I'm applying a single force F naught like this on it, then apparently it is creating an acceleration which is given to me in the question itself. It says that the acceleration is 5 meters per second square. So if you apply Newton's second law over here, the second law of a statement सीख जाएगा that the net force should be equal to mass into acceleration, because the mass is constant, obviously. So when you look at all the forces acting on the body, you realize here that yes, F naught is not the only force which is acting, but F naught is the net force, because on this body there is weight acting vertically downwards, and the normal contact force that the floor is applying, these two forces are cancelling each other. So what is happening is there's a combination of three forces acting. Okay, so this F net is the sum, the vector sum of all forces, which I'm showing in this diagram. So now notice what is happening, that in this diagram, N equal to mg, these forces cancel each other. So therefore, my net force is of magnitude F naught along the positive x-axis. If I'm taking this as my x-axis, this is my y-axis. So that is the concept I will use for solving this question. Okay. That even though there are three forces acting on the body, but the resultant net force is only F naught, the horizontal force. So that should become equal to mass into acceleration. So the acceleration should be equal to F naught by m, and that is given to me as 5 meters per second. So that is the first equation that I have. That F naught by m is equal to 5, because that is given to me in the question. Okay. Now in the second case, what we have to do is, or in the A part of the question, now we are applying the forces like this. We are applying the two forces of F naught each in magnitude, but we are applying them perpendicular to each other. So on this block, you can see we are applying two forces of magnitude F naught each, but perpendicular to each other. You can see that we are applying this force is also F naught in magnitude. Let me just show the magnitude again. This is also F naught in magnitude, but they are acting at 90 degrees. So here what is happening? The net force is going to become root of f naught square plus f naught square, or f naught, because if this is your, let's say, your force number f1, this is your force number f2. As a vector equation, your net force is f1 plus f2. Okay. And you can see that magnitude of f1 is equal to magnitude of f2 is equal to f0, and theta is equal to 90 degrees. So by applying the principles of vector algebra, you will see that the net force is along this sort of direction. So the acceleration will also be along this sort of direction. Let's say this time the acceleration is a1. So this net force should be equal to mass into a1. So the acceleration in this case should come out to be f0 root 2 by m. So that will become 5 root 2 meters per second. Using equation 1, we would see that f0 by m was 5. So now that just gets multiplied by. Yes, so that's the same thing, not much difference. Whether you say f by m is 5 or you say f is equal to 5, it's one and the same. Very good, so that's the correct method. Now let's come to the B part. That is the part I believe some of you might have had a little bit of difficulty with, so let me discuss. So the B part now, what is happening is, on that surface, again that block is there. But this time, I am applying a combination of forces in a slightly different manner. I am applying two forces like this, such that this one is of magnitude 2f0 and this one is of magnitude f0. So force f1, and this angle between them is 45 degrees. Very good, that's correct. That's the correct method of solving. So f1 का magnitude यहाँ पे कितना हो जा रहा है, f0 हो जा रहा है, f2 का magnitude कितना हो जा रहा है, 2f0 हो जा रहा है, and the angle between them is 45 degrees. So your net force is the vector sum of f1 plus f2. So that is here implying that the net force has a magnitude of f0 square plus 2f0 का whole square plus 2f0 into 2f0 into cos 45 degrees, which you know is 1 by root 2. So you take your f0 common here, you get 1 plus 4 plus, this becomes 4 into 1 by root 2, so 2. So you can take that approximately as f0 into square root of, take root 2 as 1.4, so this will become 1 plus 4 plus 2 into 1.4, so that is 2.8. This will become approximately f0 into square root of 7.3. Okay. So this is your net force. So your acceleration, let's say P2, will become the net force this time upon the mass. So its magnitude will be f0 into root 5 plus 2 root 2 divided by m, which you can write approximately as f0 by m, root 7.8. Okay. So further, if you do an approximate calculation of this, it will come out to be according to how the answer is. So this is approximately 5 multiplied with the square root of 7.8. Multiply that with 5. You get 13.96. This is approximately 13.96, or you can say approximately 14 meters per second. So the thing is, you can leave the answer this way, that's fine. You can just leave the answer this way, that A2 is equal to 5 into square root of 5 plus 2. This is also fine. There's nothing wrong with this answer. There's just then using the value of root 2 as 1.4, this approximation. That is the triangle of vector addition. Cos theta हम क्यों use कर रहे हैं बेटा? Because we are doing this thing now. We are doing vector addition over here. Just a moment. We are using triangle law over here, that magnitude of A plus B is root of A square plus B square plus 2AB cos theta. You understood your? We use cos theta, ना? यहाँ use तो किया. People hope this question is fully clear to you. Okay. Now see, I could have also done this question by using component algebra. I could have taken this as my x-axis. I could have taken the perpendicular direction to this as my y-axis. I could have solved the problem this way. That we have done by component method. So I could have said that when you are viewing that block from the top, see this is the horizontal xy plane. So your force F1 was acting like this at 45 degrees, and its magnitude was F0, and your force F2 was acting like this, its magnitude was 2F0. So you could have written the forces in component form as F0 1 by root 2 I cap plus 1 by root 2 j cap and 2F0 I cap. So my net force, which is the vector sum of F1 plus F2, would have become F0 into 2 plus 1 by root 2 I cap plus 1 by root 2 j cap. So my acceleration would have been this net force divided by the mass. It would have been F0 by m into 2 plus 1 by root 2 I cap plus 1 by root 2 j cap. Okay, so this would have been 5 in meters per second. So the magnitude of the acceleration would have become 5 into square root of 2 plus 1 by root 2 whole square plus 1 by root 2 whole square. So that would have been 5 into square root of 4 plus half plus 2 root 2 plus 1 by 2. That is 5 into square root of 5 plus 2 root 2, which is approximately again simple. 5 into square root of 7.8 or approximately 6. Okay, so this is the alternate way of doing this by component. I solved this by triangle law or by component algebra method. So both the methods you can just review at once. No hurry, okay? We have a lot of time to discuss them. So this I have solved for the net force by using triangle method. And below I have used the component algebra method. Okay, so the main thing here you have to connect with the previous chapter. Previous chapter में vector addition दोनों methods से सीखे थे. Triangle law for adding two vectors as well as the component algebra method for adding vectors. So either of the two can be used over here to calculate the net force, and from that then you apply the Newton's second law that the net force is equal to the rate of change of momentum or mass into acceleration in this case. Okay, people, so hope this is clear. Okay, so is the first method, the triangle law method, clear to all of you people? F by m हमने निकाला था ना बेटा, from the information given in the question. Devansh, F by m was given to us in the question as 5 meters per second. Okay. So the question only gave us given that F naught by m was equal to 5 meters per second. Because the first line of the question said that when a force of F naught acts, it creates an acceleration of 5 meters per second. Yeah, that's okay. As long as you understood. So the part A of the question also, if you missed, then don't worry. Take a look at the recording later. This was part B of the question. Question number 2, part B. So here below I have solved it by now the component method instead of the triangle law method. So by the component method, you will write your F1 and F2 in component form using I cap, J cap, unit vectors. Alright, so that was question number 2. Okay. So next I'm going to come to question number 5. Yeah, so I'll come to question 8. Okay, let me also discuss question number 5 first. So question 5 says that in order to drag a 100 kg log along the ground at constant velocity, you have to pull on it with a force of 300 newtons horizontally. So what is the resistive force by the ground? So let's say this is the side view of your log. So let's say this is your wooden log. It's basically a cylindrical kind of shaped object. Cylindrical shaped object on the ground. So now in order to pull it along the ground, even at constant velocity, because the ground is rough, we are assuming that it's a rough ground, so it's not smooth. So it has friction. Okay, so friction is present on the ground. So in order to move it, first of all, you have to apply a pulling force. Let's say you are pulling this with some amount of force. Now it says that when you apply the force of, how much is it? 100. You have to, when you apply the force of 300 newtons, this is moving at uniform velocity. And the mass of this is 100 kg. It says that when the external force we apply is equal to 300 newtons, the log moves at a uniform velocity. So that means that uniform velocity means acceleration is zero. If v is constant, in kinematics, you know, acceleration is dv by dt, instantaneous acceleration is, so that is becoming zero because v is constant. So that means the net force on the block must be zero. So that means this force that you are applying as the external agent, that is getting cancelled by another force, which now the ground is applying. As it is slipping in that direction, the ground is applying a force of friction, or what they call the resistive force. In this question, they are using the language of resistive force. It's basically the friction. You can see that net force 0 q है पे, क्योंकि जो external force मैं use कर रहा हूँ, that is getting balanced by the resistive force of the ground. So the amount of friction or resistive force is how much? It is 300 newtons. Yeah, Nitish, I'll tell you about question 4 also. Okay, let me make the course. Okay. So what is the resistive force? That is done now. That is the part B of the question. Now the part B is that what force must you exert to give it an acceleration of 2 meters per second. Now, second part, I want to increase the force to how much so that the acceleration becomes now 2 meters per second. So that same object now, same thing, but we are increasing the force. We are increasing the amount of force here applied now. So let's say F prime instead of F. So that it now has an acceleration. It is not 0, but rather 2 meters per second square. But in the meantime, what will happen is that the resistive force the ground is applying on the friction, that will remain the same. So this friction will be equal to 300 Newton. From part A, we have understood that. So now you apply the concept again that net force is equal to mass into acceleration. And the mass of the block was given to us as 100 kg. So the net force this time will become F prime minus the friction or the resistive force. So that should be equal to 10. So substitute the values. So F prime minus 300 to become the mass, which is 100 kg multiplied by the acceleration. This is kilogram meters per second square. And in newtons, so F prime become 300 plus 200 or 500 newtons. So you know that 1 Newton is equivalent to 1 kilogram meters per second square in terms of unit. Okay, so we are using the SI units on both sides. Yeah, I'll explain the first part again. Right. So in the first part, what we're doing is we are understanding the. Just imagine this as the practical situation. A log of wood is lying on a rough floor, like a tar road or a cement floor or something like that, which has a certain amount of friction. So उसको अगर आप constant velocity से भी drag कर रहे हो, you need to apply some force, but otherwise the ground will bring it to rest. The roughness of the ground or the frictional force on the ground will bring it to rest. Understood the yes? So to keep it moving at a constant velocity also we have to apply some force, and that is given to us in the question as a data, that is 300 newtons. It's given that when the force we are applying is 300 newtons horizontal, it moves at a uniform velocity. So that gives us the information that the resistive force or the friction that the ground is applying must be 300 newtons. This is the friction or resistive force applied by the floor on the log. As you are dragging it along, it's applying a friction. Yes, friction is equal to the external force because the net force is 0. Because the acceleration is 0. Why is the net force 0? Because the acceleration is 0. So from this statement that acceleration is 0, we are getting this statement that net force is 0. So how much is the net force now? It is this minus this. So that should be 0. So that's why the resistive force is. But in the second part, when we increase the external force more than 300, we will get some acceleration. Now the question is how much we should increase it so that the acceleration we get is 2 meters. And that is what we solved below. Meaning it is moving better, but it's moving with constant velocity. It's moving with 0 acceleration. So 0 acceleration also means net force is 0. No, Shristi, see what is happening. It's not that we are adding. See, the net force that is acting, that is mass into acceleration. That is equal to 200 newtons. Okay. But net force kya hai? Is it the force F we are applying alone? No, no. It is F minus the friction. Because the moment we are applying some force in this direction to make it move, there is friction acting in this opposite direction. Okay, yes, ma'am. Shristi, is this clear? So that is why, because this itself is 300 newtons. Huh? So then this has to be more than 300 newtons. Otherwise, how it will accelerate in this direction? And Yasmin, hope the point of constant velocity is clear to you. So, kya hua hoga na? See, if the log was at rest initially, yeah, Aditya, in this question we will not talk about coefficient of friction and all that. Okay? That will come later. You've just been asked to find the resistive force. Okay? You can find the coefficient of friction, but that we have not learned yet as a concept. So I'll come to that later. It's just about applying the Newton's second law. Abhi tak hame kya karna hai? Just simple, we have to stick to the things that we've learned, which is what that Newton's second law, that net force is equal to mass into acceleration. Okay? Yeah, now Aditya, Yasmith, coming back to your point that how the block is moving when the net force is 0, that's a good question actually. So to explore that, we have to understand कि suppose देखो block initially अगर ground पे rest पे है, okay, and then I'm applying a force of 300 newtons and the friction is also 300 newtons. You're very correct. It will not move. So what I'd have to do is first I have to apply a force of more than 300 newtons for some time, so that from rest it develops an acceleration and it starts moving with some velocity v. So at t equal to 0, if it started from rest, but I'm applying a force of more than 300 newtons, then it will start accelerating. So at some time t, it will have a velocity v equal to et. Now suppose that velocity is the value which is reached, which is the velocity I want. So तब मैं क्या कर रहा हूँ, force को वापस 300 newtons कर दे रहा हूँ. So अब क्या हो रहा है, इसके आगे से लेके acceleration 0 हो जा रहा है. So from this point onwards, it's having a uniform velocity. ठीक है? Yasmin, have you understood this point now? Yeah. It's a good point you raised, that how come the block was moving if the net force was 0? So obviously that means when it was at rest initially, we had to apply a force which was more than 300 newtons. Because 300 newtons को तो friction अकेले खा जाता है. So there would be no acceleration. It would continue at rest. But once having set it into motion, to maintain a constant velocity, how much force we have to apply? We have to apply that much force which will balance the friction. So friction is equal to the amount of force we apply. Now see, all those things we will learn better later. The friction कितना होता है, क्यों उतना होता है, how it depends on the mass of the body, how it depends on the surface. Like the same log of wood, suppose you are dragging it along a concrete floor and we are seeing that the friction is 300 newtons. Now you change the floor from concrete to, let's say, marble floor, or you change it to a glass floor, or you change it to something else, or you change it to a mud floor, like a clay floor. You will see the amount of friction will change. So it depends on various things, and that we will learn in future. But as I said, right now in this assignment and for the beginning of this chapter, we are keeping things very simple. We have to just understand how to apply Newton's second law, that is net force is equal to mass into acceleration. Okay, sir, is the point clear? So to answer your question, on one surface, the friction need not be the same because it also depends on the block's properties. Okay. All right. So that was the fifth question. Now, Nitishi, you have asked about the fourth question, so I'll quickly give you a hint. So fourth question में बेटा देखो आपको कैसा करना है. It is given to you that it is moving along a straight line through a distance of 8 meters in 6 seconds. Okay. So Nitishi, in fourth question, what you have to do is you actually have to use kinematics to find out the acceleration of the body, and then you have to apply Newton's law that F is equal to ma. So in fourth question, it is given to you that it's starting from rest at t equal to 0, and then it has a displacement of whatever 18 meters at time, what is it, 3 seconds, 6 seconds, something like that. Again, 6 seconds. So from this data, I will find out the acceleration using kinematics, that S is equal to half at square, because U is 0 and acceleration is constant. Because U is 0 and acceleration is constant. Why? Because we are applying a constant force. So from this, I will find out acceleration. Okay, how much acceleration is, and once I got the acceleration, I will get the force as mass into acceleration, or I'll get the mass of the body or whatever. Okay. So it's like an indirect question like that. Okay. Now I'm coming to seventh question. So question 7 is again a question where it's not really based on the principle that you have learned, but it is more about how to apply what is given in the question. So question का language आपको बहुत ध्यान से पढ़ना है और उसको interpret करना है कि कैसे it's happening. So it's saying that the gravitational field of the earth at a height h above is written such that g at a height h is equal to g at the ground level into this factor, which is radius of the earth square upon radius of the earth plus h whole square. Okay. And for example, you know that the value of g at the surface of the earth is about 9.8 meters per second square. Okay. Or more approximately, we write it as 10 meters per second square. You also know that the radius of the earth is approximately 6,400 kilometers. So now based on this formula, so where this formula has come from, that is not important for us right now. Okay. It's just that the question has given us this formula, and given this formula now, we have to find out — 6370 is given, is approximately 6400. So we have to find the weight of the person in newtons and pounds at the Earth's surface. Okay. So weight क्या होता है? Weight is equal to mg. So at the Earth's surface, okay, h is equal to 0. So g's value we'll take as g at h equal to 0, which is acceleration due to gravity on the surface of the Earth. अच्छा dyne नहीं पता, I'll explain, don't worry. Meters per second square. So the weight of the person mg will become mass, which is 80 kilograms into 9.8 meters per second square. So it will become nearly 800, very nearly 800 newtons. Now the other thing is not very important for us, but you should know, okay, that you can convert newtons to pounds. So 10 kg of mass, or rather 10 pounds, is equivalent to 4.5 kgs. So this is the conversion factor, or 1 kg is equivalent to 10 upon 4.5, or you can write that as 100 by 45 or 20 by 9 pounds. Now the thing is, 1 kg is equivalent to a weight of approximately 10 newtons. Okay. So now you'll understand like this, that 10 newtons is equivalent to 20 by 9 pounds. Okay. So there we have 80 newtons is the weight of the person. So that is equivalent to 80 into 20 by 9 in pounds. Okay. This lbs is the symbol used for pounds. Pounds is an outdated unit that is not used anymore in engineering and science, other than for very specific purposes. kg and pounds का relation बेटा ये है. This is the relation, that 10 pounds is equivalent to 4.5 kg. So if it comes in the exam, beta, the relationship will be given to you between pounds and kg. You don't have to memorize it. Yeah, imperial metric system. That's correct, beta. Aditya, that's correct. Okay. Okay. Now let's come to the next thing. Now the next thing is quite involved in calculation. So you have to find the weight of the person. Weight of the person whose mass, by the way, is 80 kg at a height of 300 kilometers above of the Earth's surface. Okay. So for this you have to use the formula. The formula of G that is given to you. G at the height h is G at the ground level into radius of the Earth, that is given to us as how much now? 6370 divided by radius of the Earth plus this squared plus 300 whole square. So this is 9.8 into 6370 upon 6670 whole square. So this is a very tricky calculation, okay, but you have to actually do this. So this will give you, yeah, I'm coming back to that in a moment. And once you got that, you will get the weight of the person at that height h. It will become 80 kilograms multiplied by this factor. This will be the exact value of the height weight in newtons. Okay, so let's just go through both the parts once more. So part A was weight at ground level. That is H equal to 0. The mass is given to us 80 kg. So the exact value of weight actually will be 80 into 9.8, which will be this 784 newtons. This will be the exact value. And this will become the conversion. So this was 800. So this is pound isn't used anymore because it is an outdated system. Right? It was based on the old British imperial system, and since the standard international system of units has taken over, okay, so we don't follow it anymore. Okay. There are some historical reasons and all, and you can research that actually. You can tell me about that also, what the exact historical reasons are. But fact of the matter at the end of the day is that it's not used anymore. Okay. So don't worry about the full calculation. You can use a calculator and do it over here. In JEE, you will not typically get questions which have so much calculation involved. It's just more for your general knowledge. Okay, now let me come to the 8th question. The third part of this, what about the mass? So for the third part, you have to understand that mass m, which is equal to 80 kg, is independent of gravity. It is independent of the value of g. So the mass will be equal to 80 kg whether you are on the surface or you are on the height h, or you are even in outer space where you are so far away from Earth that there is no gravitational field of the Earth. कहीं पर भी हो, but mass same रहेगा. Mass is a property which is independent of gravity, of gravitational field. Okay, so that's just a factual matter that you should know, that mass is that inertia of rest property which holds independent of gravity. A body which has a certain amount of mass will oppose the change in its state of rest through its mass by the same amount, whether or not we are on the Earth's surface or on the Moon's surface or in outer space where there is no net gravity and things like that. So it's independent of gravity. It's a fundamental property of the body. Mass is to do with amount of substance within the body, and that is independent of. All right, now let's come to the next question, which is the important one I want to discuss, question 8. Okay. So I understand many of you have had a bit of difficulty in how to apply the concept we have learned so far. Okay. And you might think that, okay, out of the concepts we learned in the first lecture, might be difficult to solve this problem, but the thing is, I'll show you it's not that we cannot solve. We have to just systematically apply the Newton's second law concept over here. So as a smooth surface space, there's a combination of two blocks. So this one is of, let's say M1 is of, right, this is labeled M1. Anyway, just given 2 kgs. So okay, this one is of 1 kg, and this is a smooth surface, so no friction. Okay. So remember, this is a very ideal case. Actually, all surfaces have at least some minimal amount of friction. But extreme cases like an ice skating rink, and you have some very slippery object on it and all that. Yeah, you can do that. So okay, but I'll tell you the systematic way of solving this. Okay. So the systematic way of solving this is like this: that when we apply a force, a horizontal force of 5 Newton is applied on the block P, and the block A is against the block B. So what ends up happening here is that you are pushing block A. So let's with this force. So what happens is the block A ends up pushing the second block with some force. So I'm showing them at a distance, but actually they're not at a distance. So block A ends up applying some force on block B. He applies some kind of what we call a contact force on block B. So this one is the normal reaction. Contact force with which A is pushing B as a result of you pushing me. And then what will happen? B will react back on A by applying an equal and opposite reaction force. So B will now apply a force on A, which will have same magnitude. So this is an equal and opposite normal reaction force. With which B pushes back E. So it's just a matter of diagram I'm showing you separately, but actually what is happening, the two blocks are against each other. So a more accurate way of representing these two things happening together would be something like this. So we talk about all sorts of forces which are acting here in this system. You see that of course there is weight of E. This is M1G, which is pushing it against the floor. So the floor will react by applying an equal and opposite force on this one in the upward direction. So the floor will be applying some kind of force like this. So as a force like that. This is, let's say, normal reaction on E because of the flow. And that's why E is not moving vertically, because ये normal reaction उसके weight को balance करता है. And likewise, B is also having its weight pulling it down with the force M2G. But again, why it's not going down? Because it's supported by the ground. And the ground is applying some kind of normal force like this on B. Okay. And if we were not applying any horizontal force, this is what would happen. There would be no other force. But अब क्या हो रहा है? इसके साथ में I'm pushing this system with a force F like this. So the moment I'm pushing this with a force F like this, A starts pushing B. So what happens is A is now applying a normal contact force on B. So you can say this is the force on B by E. And obviously by Newton's third law, B pushes back E with an equal and opposite force like this. So it's same magnitude but opposite in direction. So this is the force on E by B. So these are all the forces which are acting within the system. Okay, so these are, you can say, the forces in the system consisting of the blocks A plus B. Okay. Now we'll also realize that as a result of these forces, there's no friction on the ground. So they both start moving with a common acceleration E. Okay, so the important thing here is that A and B will have common acceleration. start slipping but remaining in contact. They don't come out of contact. So because they are remaining in contact, we can say that they'll have common acceleration. Therefore, they have identical accelerations. Both of them. Okay. So now if I apply, some next thing is now apply Newton's second law individually to each block. So this is where the application of what we learned the last time comes in. Every action has an equal and opposite reaction. So we have on the block E, we have the external force, the normal reaction with which this is pushing back its own weight, and the normal reaction that the ground was applying. Let's say like this. So what happens is for E, N1 balances weight, or in other words, N1 is equal to mg. But this one doesn't balance this, because we can see that the block is accelerating. So what will happen? But F will be greater than N, so there is horizontal acceleration. There is horizontal motion, such that net force, which should be equal to mass into acceleration. That equation here becomes F minus M is equal to M1, or F, which was, how much was it? 5 newtons. So when we substitute this numerically, we have 5 minus N is equal to 2E. That becomes our first equation, which we got by applying Newton's second law to the block P. Okay. Now likewise, I will also apply Newton's second law to the block B. And let's see what that will give us. So block B पे क्या हो रहा है? Actually life is a bit simpler. There's only one horizontal force acting on B. On the block B, we have only one horizontal force, and that is this normal reaction. इसका action reaction पे, and that is what is giving it the acceleration P, because the vertical forces are again balancing. इसका जो weight है, that's again getting balanced by whatever normal contact force with the ground. So N2 balances M2G. So this is why there is vertical equilibrium. There is no motion in the vertical direction. Okay. Whereas the normal reaction N pushes the block B, such that N is equal to M2G. So substitute the mass. So N is equal to 1, sorry, not G, 1 into E. One kg into E. This is our second equation. Now solve equation 1 and 2. So 5 minus N is equal to 2A, and N is equal to E from here. So add the two equations. You get 5 is equal to 2 plus 1, that is 3A. So the common value of acceleration is 5 by 3 meters per second. So this is the so-called common acceleration of both blocks. Okay. And substitute this back in equation 1. So N will become 1 kg multiplied by the acceleration. That is 1 kg into, so 5 by 3 meters per second square. So N is equal to 5 by 3 newtons. Okay. Or you can substitute in the second equation. Or we have F minus N was M1E. So F was 5 newtons, M1 was 2 kg, and this acceleration was, you just saw, 5 by 3. So you can do this also. So N will become 5 minus 10 by 3. So that will become 5 by 3. Okay. But in newtons, that's the same thing. So this is the normal contact force between the two blocks. Now, I know some of you might have solved this by combining the two blocks and all that. Those are more, you can say, elaborate methods of solving the problem, and we'll be discussing many such things as we go along. But as of now, I wanted you people to solve this by the application of the fundamentals, which is Newton's second law applied to one block at a time. So I want you to understand this method in detail first, okay? Without getting into combining the two blocks and things like that. Just apply Newton's second law very simply to each block separately and understand how the net force on that block is becoming the product of its mass and acceleration. So just go through these diagrams and explanations first. Yeah, that is the thing. So there are certain conditions in which we can do that. We can combine the two blocks, and certain conditions in which we cannot. So I will be discussing such things in detail as we learn more things about Newton's laws. Okay. But just to tell you as a rule of thumb, if two blocks are moving together such that they are in contact and having common acceleration, then we can always combine them and make them a single block. Yeah, I mean, we have understood the application of Newton's third law, the action-reaction principle. Why there's a pair of normal reactions acting between A and B. A is pushing B forward and B is pushing A backwards with equal and opposite force. So that is the application of Newton's third law. Because we can see that we are pushing A from this side, so A will carry B with it. ऐसा तो नहीं हो सकता that when we are pushing A from this side, B will run away faster than A. They will have to be in contact. That's how we understood, Viraj, that they are having common acceleration. Because we know that they will be in contact as they move. Okay, so this point which I've written below over here, that they start slipping but remaining in contact. So therefore they have common acceleration, or they have identical acceleration because they remain in contact. If they had different accelerations, they would not have remained in contact. Okay, so this is the critical part now. Once you understood the forces, the application of Newton's laws individually to each of the blocks. Okay, now, so hope these steps are clear to all of you. Alright, so ninth question I would suggest that you try and solve yourself, because you have to just do the vector addition of F1, F2, and the third force F3 should be such that it is the equal and opposite of F1 plus F2. Okay. So in the ninth question, you can use either the component algebra method, take the x and y axis and write F1 and F2 in I cap, J cap notation and use components, or you can also go with the triangle law method. If you go with triangle law, then you'll see the angle between F1 and F2 will become 90 plus 30 or 120 degrees, and their magnitudes are given to you. So you use triangle law with that cos theta formula and all that. Okay. That's simple. Now let's come to the 10th question. So in 10th, what is happening is the forces are already given in component form. Okay. So you have to just add them. 4 kg object is subjected to 2 forces. So to imagine that there are only 2 forces acting on the body. There is no other force acting on it. So in a question like question number 4, now you just imagine that there is no gravity or anything like that. Since it's saying that there are only 2 forces acting, so the directions आपको vector से मिलेगा ना बेटा. Okay. So imagine the body is in outer space, it is just floating, something like that. And now there's a combination of 2 forces acting on it. Only 2 forces, nothing else is acting. There's no weight, there's no normal reaction, nothing like that. Because the question clearly says that it is acting it's moving under the influence of 2 forces. Now, one force you can see is given to us by the equation 2i cap minus 3j cap. So this force must be something like this. If I take this as my x and this as my y, so ये वाला force ऐसा कुछ होगा. It must be having a negative y component and a positive x component. So this force must be something like this. And the second force is having positive x and y components. So that one is, let's say, something like this. This is the second force F2, which is given to us in equation form as four I cap plus 11 j cap in newtons. This is also newtons, this is also newtons. And the mass of the body is given to us as m kg. Oh, sorry, 4 kgs. Okay. And the object is at rest at t equal to 0. So mass is equal to 4 kg. And initial velocity is 0 at t equal to 0. So क्या होगा यहाँ पे, the net force which will be acting on the body will be the vector sum of these two. So just calculate the vector sum now. They are given in component form, so just calculate. So it is 6 I cap plus how much? 11 minus 3, so that is 8 j cap. You can see the net force is this much. So the net force is some, like, but to draw the parallelogram, let's say something like this. So ऐसा कुछ होगा net force, suppose this is your net force. So it will have an acceleration also along this direction. So the acceleration will be net force divided by mass. Okay, sir, we shall come to that. Okay. So net force was 6 I cap plus 8 j cap in newtons divided by the mass, which is 4 in kilograms. Okay. So the acceleration is 3 by 2 I cap plus 4 j cap. The acceleration magnitude that will be 9 by 4 plus 16. So 2. I can state here this. Eight by 4, so that will become 2. So that is square root of 16 by 4. Sorry, 9 plus 16 by 4. So that is 25 by 4. Okay. So the magnitude of acceleration is becoming how much? It's becoming 5 by 2 meters per second square. Simple. So nothing, you just had to apply this thing, that net force is F1 plus F2 and carry out that F1 plus F2 operation. So that is the acceleration. So the velocity at 3 seconds will become how much? Now u was 0. So velocity will be acceleration into time. So as a vector, it will become 3 by 2 I cap plus 2 j cap into what is the time? So this is in meters per second square, and the time is in 3 seconds. So this will become 9 by 2 I cap plus 6 j cap in meters per second. That will be the velocity as a vector quantity. Whereas if you want the magnitude of the velocity, dEt. So it's 5 by 2 into 3, 7.5 meters per second. Numerical values he used here, beta. So we have used the numerical values only to find B. We first found out the numerical value of A by using Newton's second law. Achha, on Sarvesh's request, I am going back to the 8th question, part B. Okay, so this. So you can see now on the block B, the forces are explained in this diagram. This diagram or the above diagram. This one. ये इसको push कर रहा है towards the right, and weight and normal reaction are balancing each other. So there are only 3 forces acting on the block B. A is pushing it towards the right, and then there are the vertical forces. No, our forces, where we are applying the force on B? We are applying it on A, na, Sarvesh? The force is that we are applying from the left. It is not acting on B. We are applying it on the block A, na? Okay, so that's the 10th question. 11th question is about differentiation. You should be able to do it. Okay, so you have to find the momentum at the instant at which the force becomes 0. So what is happening? I'll just give you a brief hint on how to do the 11th question. So question 11, what is happening is that the velocity is given to you as a function of time. Okay. So you can find out the acceleration by differentiating the velocity. So now you have to find force, which is mass into acceleration. So you get this. So you have to find the time at which the force is 0. So that means the time at which the acceleration is 0, or that is the time at which dv by dt is equal to 0. So given this function, if the velocity is ft, then the acceleration is the derivative of that function, the differentiation of this function. So to find this time, you put f prime t, or the derivative as 0, and calculate the time. And once you got the time, plug it back in the equation of velocity, and from that you will get momentum. Momentum p is equal to mass into velocity. So put this value of time that you get on solving this. Okay, yeah, very good. Back in this equation, so you get the velocity at that moment, and then multiply it with the mass, so you get the momentum. So that is 11th question. Very similar is the 12th question also. Same thing basically, but a more complex function. Okay. So 11th and 12th, I hope you people can manage. Okay. Does anybody have a doubt in 13th question? Okay. So let me explain 13th question. So in question 13, it's like this. Imagine the barrel of the gun, or what is called technically, in technical language, is called the muzzle of the gun. So I'm not drawing the whole gun. Personally, I'm very against guns. So, but anyway, so this barrel or muzzle of the gun this is of a length L given to us. and the speed with which the bullet comes out over here, that is called the muzzle velocity. So this bullet comes out with the speed v, that's the muzzle velocity. And obviously the bullet starts from rest over here. So if it starts from rest over here, you can see that the average acceleration is suppose e. Then v square should be equal to 2as, or that a should be equal to v square by 2l over here, because your u is 0. So that is your average acceleration. So therefore average force So again, it is basically a matter of kinematics. You have to apply kinematics to solve this. So this was question 13. Okay. Question 14 is very simple again. You have to just use addition of vectors. So you can see the maximum magnitude of net force will be when the two forces are parallel. And that is when it will become 5 plus 4 or 9 newtons. Minimum will be when they are opposite each other. That is in the second diagram. That time 5 and force combination will give you a net force of only 1 newton. Whereas the 90-degree case will give you square root of 25 plus 16. And the 30-degree case will similarly give you something, take cos 30 as root 3 by 2. And 15th question again, you have to use addition of component algebra of vectors to find the net force, and then use the equation net force is equal to mass into acceleration. So that completes the discussion of the worksheet. Just go through these couple of questions and we will start with the next section. Just a minute. Okay, now moving on to the next aspect of Newton's laws of motion. Now, when we talk about forces in general, we have to understand one thing, that Newton's second law has defined the relationship between net force and the rate of change of momentum. Okay, so second law has given us this relationship that the net external force acting on the body is equal to the rate of change of its linear momentum. But the question still remains that what exactly is force? This is talking about net forces. So why did you know all the individual forces acting on a body? It doesn't really define what force in itself is. So we have to understand what is a force. What is a force itself? So that we understand, a force is nothing but an interaction between two bodies or particles or even two systems. You can even say it is the interaction between two systems. So what do we mean exactly by interaction? So for that we have to understand what are the fundamental type of forces. So the fundamental type of interactions known in physics. Okay. So I am talking about the absolute fundamentals. That what type of forces do we observe in the natural universe. Then we'll come to things like mechanical forces, contact forces, friction, etc. So fundamentally in the universe, like I explained to you in the very first lecture that we discussed about the scope and the width of the subject of physics, we had understood that there are four types of fundamental forces. The first is the gravitational force. The gravitational force is due to the gravitational attraction between any two masses. So basically gravity comes from the fundamental property of mass. In a later chapter we'll study about this and we'll understand that any particle having mass m1 in the vicinity or close to another particle having mass m2, and if they are at some kind of distance r, they in fact fundamentally they have the property of interaction, which is called the gravitational interaction, which is always an attractive force. Fundamentally gravitational force is always attractive, it cannot be a repulsive force, and they experience a force which is directly proportional to product of masses and inversely proportional to square of distance. Okay. So this is a fundamental observation in physics. About nature of mass and through it gravity. It doesn't come from anything else. It just comes from that property of this. So that is the one of the four types of fundamental interactions or four types of fundamental forces which are known in physics. So I'll just leave you to note down this part a little bit first. Then I'll tell you about the other three. Yes, that is correct. Rate of change of momentum, Sarvesh, we have studied that in the first lecture. P is linear momentum, mass into velocity. Yes, correct, yes, ma'am. Denominator of this, it is r to the power 2, where r is the distance between the two particles. This is the gravitational force. This is the gravitational attraction force between two particles of mass m1 and m2 at a distance r. Yeah, capital G is it's called the universal constant of gravitation, and that is the constant of proportionality. That is correct, Sumit. Okay, so in fact, this becomes where capital G is the universal gravitational constant. But we don't need to get into all this right now because this will be a later chapter. Okay. Now, what is the significance of gravitational force for us in mechanics over here? Is that the Earth is such a huge mass that on the surface of the Earth, it's only the gravitational pull of the Earth that matters. So, when when considering forces on a body of mass m on the Earth's surface, the weight of the body, which we write as mg, is nothing but the gravitational pull or attractive force on the body due to the Earth's mass. Okay. So if we are looking at it from an outer reference where we are looking at this from far away, so this is the entire Earth, which has mass me, let's say. Okay. Now the mass of the Earth is very, very large compared to the mass of any body. Like we were discussing action-reaction principle last time. So mg is nothing but the gravitational pull that the Earth is applying, and it will always act in such a way that it will act like this. It will, as if the force vector will be directed towards the center of the Earth. So this is the center of the Earth. The gravitational force that the Earth is applying. This is the gravitational force on the block or particle or whatever due to Earth. Its direction will be towards the Earth's center. So it will be perpendicular to the surface. So it will always be vertically downwards. And of course, its magnitude will be equal to mass of the particle into g, where g is equal to acceleration due to gravity on the Earth's surface. Which is approximately 10 meters per second square. Or more appropriately about 9.8 meters per second square. So the thing is now, see, we are actually on the surface of the Earth, and compared to our dimensions, the radius of the Earth is so large. So that is why when we observe that body, it doesn't appear to be towards the center of the Earth in that sense. It just appears to be vertical. So for us, what is happening in that reference frame? In that reference frame, the surface of the Earth will appear to be a plane horizontal. This will be a horizontal plane. So any body, if its mass is m, the gravitational force will always act like this. It will act in a direction which is perpendicular to this, or it will be vertically downwards. And that is irrespective of anything, whether the body is like this, or we might consider there's another body lying on an inclined surface. So it's in fact accelerating down like this, but that does not affect the gravitational force. The gravitational force इसमें भी vertically down ही act कर रहा होगा, और उसका magnitude mg होगा. It's irrespective of everything else. Or we might have taken an object and we might have projected it. Suppose we projected it like this from the Earth's surface. So it's going in projectile motion. So after some time it is over here. Its velocity is in this sort of direction, but still the weight acting on it will be independent of all this. So whatever the state of body or the particle, the weight is equal to mg, and it is vertically downwards. At the Earth's surface. So this fact here, the value of g, it will change. It will only change if we are at a significant height. H, where h is order of magnitude should be greater than 100 kilometers and more, or significant depth. Again, where d's order of magnitude should be greater than hundreds of kilometers from the Earth's surface. So in this chapter, for all practical purposes, we consider the system in which we are dealing is not at a very huge height above the Earth's surface, or not at a great depth below the Earth's surface, kilometers or thousands of kilometers. So we take mg as an invariant force. It does not vary. Okay, so mg is like an invariant force. Whatever state the body is in, whether it is in motion, whether it is at rest, whether it's sliding down an inclined plane, whether it is going in projectile motion, whatever it be the case, mg is independent of all that. It is only dependent on two things: the mass of the body and the acceleration due to gravity of the Earth, which is constant, of course, and its direction is vertically downwards. Yeah, Yojit, so Big Bang theory is about the interaction of fundamental particles at the birth of the universe. Okay. And those interactions are what resulted in the fundamental type of forces. So it's like, subnuclear particles consist of baryons, fermions and all that. And nuclei consists of the subnuclear particles. Then nuclei and electrons together constitute atoms. So each layer of interaction is happening at the fundamental level because of the interaction that happens between fundamental particles of nature. Yeah, I'm coming to the note. Okay. So this is before that. This is fundamentally what we need to understand about this. The weight of a body for an experiment conducted on the surface of the Earth. Yeah, so Yojit, anywhere on the surface of the Earth, the acceleration due to gravity is more or less constant at 9.8. Now remember, I'm saying more or less constant. That means there are some variations to it, and that we will see in more detail in a chapter called gravitation. Like you might have heard that acceleration due to gravity at the poles is slightly larger than what it is at the equator. But those are minor variations, very small percentage changes. So here in this chapter, we'll assume that the value of g, acceleration due to gravity, is independent of where on the earth we are, which latitude and what longitude. That is not affected by it. It remains constant everywhere on the surface. On the moon, it will change surface, obviously, because mass of the moon is different, radius of the moon is different compared to the earth. Why on the moon? Even if you go to something like 1,000 kilometers above the surface of the earth, you're on a satellite or something, there's a significant change in the value of acceleration due to gravity. Okay, people, so hope you understood about gravitation, which is the first of the fundamental types of interactions known in physics. All right, now the second type of fundamental interaction known in physics is electromagnetic interaction or forces. So, yeah, Sarvesh, I'll provide you with the notes, so don't worry, you can go through that part later. So, electromagnetic interaction is basically the interaction between charged particles. Namely, yes, Yashmit, it does. So on a planet which is heavier than Earth, the acceleration due to gravity will be more. So if you're standing on the surface of a planet which is heavier than Earth, then you will weigh more. Your mass will be the same, but the weight you will feel will be significantly more. Similarly, if you're on a lighter planet where the acceleration due to gravity is less, then you will weigh less, even though your mass is the same. And that is why you're seeing photos of astronauts jumping around on moon, because the same amount of mass of their body, but the weight is not less. It's less by about a factor of 1/6. Whereas if such astronauts were to go on the surface of Mars or something, where the acceleration due to gravity might be larger, their same bodies will weigh them down with more force, more weight. So it will be more difficult to move around. The same amount of muscular effort will result in smaller steps, whereas on the moon, the same amount of muscular effort is resulting in much larger steps because your body is weighing less. These are some of the interesting things about gravity, and you will learn more about all these things very soon when we come to the chapter of gravitation. But currently, let's stick to what we're doing here. So, electromagnetic forces are basically the interaction between charged particles, namely electrons and protons. Whereby electromagnetic forces are in two types: electrostatic forces. So, that is forces between charges at rest with respect to things. And magnetic forces, this is the same magnetism that you have studied about in 9-10 from magnets, but it is more general actually than that. So magnetic forces are the fundamental forces between charges in motion. Okay, so collectively we call them interactive. We call them electromagnetic forces. Now, the forces because of charges at rest and the forces because of charges in motion. So they are basically interaction between charged bodies or charged particles, and they are called electromagnetic force. A good example of this is the Coulombic attraction on orbiting electrons inside an atom due to the nucleus that is having positive charge. The electrons are negatively charged, which you studied about in structure of atom. So the nucleus is having plus Ze kind of charge, and if you have an electron having negative E charge in an orbit of radius r, so you've seen that the electron experiences an attractive kind of force. And that attractive force is then proportional to Ze square upon r square. So at a later stage, we'll study something called Coulomb's law. If you're interested, you can start reading about this. You will find this in Resnick Halliday book or H.C. Verma part 2 and all that. But to answer your question, Bermuda's triangle, the real discrepancy in Bermuda's triangle is more to do with the magnetic field of the Earth over there, rather than gravitational field. Yeah, you studied about Coulomb's law in structure of atom. So, but it's actually Coulomb's law in detail is more to do with physics, which you'll be studying later. So you'll find it in your part 2 of the books, class 12 part. But now, why electromagnetic forces I'm mentioning over here as one of the fundamental forces? Because many of the mechanical forces that we'll be studying about now, many of the common E is that electronic charge, 1.6 into 10 raised to minus 19 Coulomb. So charge of electron is minus E. Charge of proton is plus E. The charge of a nucleus is plus Z, where Z is the atomic number of protons in the nucleus. That Z, that symbol, Z is the atomic number. So this is clear. Okay. Now, the important thing for us here, why I'm talking about this here, is that any type of interaction between matter is usually a combination of electromagnetic forces. What I mean to say about that is, something very different. For example, if you look at intermolecular bonds, what are they? They are electrostatic forces. If you look at interatomic bond, they're again what? They're electrostatic attraction. If you look at contact force between two surfaces, so what really we mean by contact force? matter. This is matter. Yeah, so if we talk about contact force between two surfaces, for example, we have normal reaction contact force. So उसमें क्या हो रहा है? You have typically, let's say, an object which is lying against a surface. So this object is pressing down against the surface with some amount of force like this. At every point there's like a pressure, and that is contributing to a net downward normal reaction. Okay, so there's a downward normal reaction force on the floor. Okay, and the floor applies an equal and opposite normal reaction upwards on the block. So the block experiences an upward or a vertically upward normal reaction force. But this normal reaction force, fundamentally, what is it as a result of this? Okay. So fundamentally, where is this contact force coming from? Okay. Is it coming because of gravity? No. This is not because of the mass of the earth pulling it down. It is coming because the molecules of the surface and the molecules of the block are repelling each other. So this fundamentally, it is coming from molecule-molecule interaction at the surface of contact. And any molecular interaction that we talked about in matter, fundamentally that is as a result of what? So it is as a result of electrostatic forces, or in general we'll say electromagnetic forces. So who is the agent of normal reaction contact force, or for that matter, who is the agent of friction? Okay. It's all electromagnetic force. It's all fundamental force at the electromagnetic level. This is point clear to all of you. Another example of a mechanical force. We have a type of force called tension. Or what we call tensile force. The word tension is derived from tensile force. That acts along the length of a rope or a chain, or a thread, or any of these kind of things. When stretched out. Yes, that is also electromagnetic force. When you, for example, Sarvesh, when you are gripping a surface tension is also to do with molecule-molecule interaction. The property of surface tension is also to do with interaction between molecules. So coming back to the example of the force that you are applying with your hand. So for example, if you are using your hand to push, you are using your hand to push against an object. So again, जहाँ पे आप push कर रहे हो वो एक contact force है ना. So it is basically what it is, electromagnetic interaction. Or suppose you are pulling on a rope with your hand. So क्या हो रहा है? As you are pulling against the rope, your hand surface is actually applying friction on that surface, and through that friction it's trying to pull on the rope. So again, that is what type of interaction? It is interaction between the molecules of your hand, the outer molecules on the surface of your hand, and the molecules on the surface of whatever you're pulling. So these are all examples of what kind of molecule-molecule interaction. So at the fundamental level in physics, there are which type of interaction? They are electromagnetic forces. So now coming back to tension. Okay, so for example, you have a chain. Okay, now you have a chain like this. Now one side of it is attached to a wall. So notice that if you are pulling the other side with the force F, there is a chain. There is a kind of interaction force that acts within the chain. So the moment you are pulling with an external force, you will see that the chain is the chain stretches out and develops tension. Whereas in the same example, if the chain was not stretched out, it's just lying on the floor, let's say. So it might look longitudinal, it might still look like it's a straight line, but it's not stretched out. It might not be crumpled at one position, but it's kind of loose. So it's not having tension. So now let us understand more in detail what this tension is. So what is tension really? Let's understand this. So coming back to the first diagram. So these are, each one is a link of the chain. So they are the links of a chain on which an external agent has applied a force on, let's say, now I'm labeling this one as the first link. So this one is the second link. This one is the third link. Now if you think of the forces acting on the first link, so you see, for this one, the first link, you have applied a force like this. The external agent has applied a force like this. But do you see it accelerating like this? No, no. Because what is happening now? The second link is pulling it back. So that force with which it is pulling it back, that is called the tensile force. So this is T, let's say 1, 2. So this is T1, 2 is the tension force on link 1 due to link 2. Okay. Now similarly, you make the second one's diagram here. So this is now the second link, which is looking like this. So second link पे क्या हो रहा है? The first link is pulling back with equal and opposite force. This is T21. But now the third link is pulling this in this direction so that this does not move. This is the force on the second link because of the third. Okay. So none of these are in motion. Now this one is at rest. This one is at rest. So like that, now any general one you take, you see that it's pulled on either side with tension. Okay. So you can see here that because the chain is at rest, that means the net force on each link is equal to 0. So F is balanced by T12, that is balanced by T21, that is balanced by T23, that is balanced by T34, like this. So there is a uniform tension. So there is uniform tension P equal to F at all the links. Whereas if you are not applying the force, there would be no tension at all. So the pulling force between two links of the chain, when you're pulling this with the force F, you can see each link is pulling back the other link. Now second वाला link first वाले link को left की तरफ pull कर रहा है, first वाला link second को right की तरफ pull कर रहा है. So now the third one is pulling back the second one with a force towards the left. So those interactive forces between the links are what we call the tension. Okay. So tension is a force that develops within the chain or rope or whatever. So in this example, tension is the force that develops along the length of the chain when it is stretched. So what type of force I'm talking about along the length? The interaction force between the links. The moment the string is the chain is stretched, each link is pulling back on the next consecutive link with a force which is along the length of the chain. That force is what we call the tension. Sarvesh, we are talking about tension over here. So forget about normal reaction for a moment. Yeah, I'll scroll down. Don't worry. Archit, I'll scroll down. Okay, so let's understand this property of tension like we understood for this chain. Now let us understand tension in a rope or a string through another example. So another example of tension, let's see to understand. Now we are having this situation. From a small hook on the ceiling, we have suspended a string kind of thing over here, and we have attached a block below it. And that is also attached through a small hook kind of thing. This is in a vertical plane. So G. So this is a light thread. So what we mean by light is that its mass is negligible compared to the mass of the block below. So this is a block of mass capital M. So it's like, capital M might be a few kgs, whereas the mass of the rope or the string is just a few grams. So it's completely negligible compared to the mass of the block. So now we realize what happens is that because of the gravitational pull on the block from the earth, the weight of that is pulling down on the rope or the thread. And the rope is, or the thread is in what kind of state now? It is again stretched. Okay. So it develops a tension. So we will see that because, so here what happens is, in this case, the weight of the block literally causes it to pull down on the thread. Okay. And this causes the thread to be in a stretched state or to develop a tension. So as a result of this weight of the block pulling it down, the thread is in a stretched out state. And develops tension. Let's say T. So what is tension again? It is a force along its length. So just write down up to this point, then I will explain to you about that force more. Okay, so written this down. So now if you see what is happening within this system, if you see the thread itself, just the thread, इस पे नीचे की तरफ एक फोर्स लग रहा है बिकॉज ऑफ द ब्लॉक, और ऊपर की तरफ एक ऐसा फोर्स लग रहा है. And that is creating tension in the thread. That is keeping the thread stretched out. Whereas if you look at the block, now the block through the hook is experiencing an upward force. And that upward force is equal to the tension, because so this and this are in action reaction. Similarly, on the wall or on the ceiling above, there was a small hook. So that hook is experiencing a downward force. So you can see that this is the tension force on the block, applied by the thread. Okay. This is the tension acting downwards on the thread's end point. Okay, let's say this end is end B. This is end B of the thread. This is the end E of the thread. Okay. Applied by the block. So these two are an action reaction pair. Okay. Similarly, above here, these two, they are an action reaction pair. Okay, they are the interaction between the hook and the string itself. So here you can see that the thread being stretched, it develops tension, or what in more elaborate language is called tensile force. Along its length. Now, these type of forces also, even tensile force acting within a rope or a chain or a thread, it is happening because of what? Molecule-molecular interaction. So, fundamentally, what is tension also? Fundamentally, tension is also electromagnetic interaction. Tension is also created by electromagnetic interaction. Okay, so people hope you're understanding this part. So this chapter is like this, each little thing is has a lot of applications. So like we'll see many different situations in which normal reaction acts between two surfaces, many different situations in which tension acts on a string or a thread or a rope or something like that develops tension. But today we are just understanding the fundamental aspect of tension, what it is. It is this kind of longitudinal force or force that acts along the length of a chain or a rope, which acts because it's having a tendency to get stretched. When external forces act on a rope or a string or a chain or any such object, it causes it to have a tendency to stretch. So the molecules of it react by applying a force along their length. That force is called tension. And that tension is also as a result of electromagnetic forces. Yeah, so Viraj, that's correct in fact, that most of the forces that we see, friction, normal reaction, tension, these are all examples of electromagnetic forces. So actually it's always gravity or electromagnetic force. और अर्थ पे gravity एक ही important है, which is the weight. हाँ अर्चित, because again see tension is like the reaction of the set of molecules. ना अगर molecules के बीच में electromagnetic interaction नहीं होता, so then when you apply forces on the string from the two sides, they would just come apart. Na? The molecules would just move away from each other. The whole constitution of that material would just break apart. So why it's not breaking apart? Because there is some kind of interaction between the molecules and they're binding each other. So that binding each other is happening as a result of what? It is happening as a result of the fundamental charge of the particles with which the molecules are constituted. Tensile strength is something to do with the maximum amount of tensile force that a material can experience before it breaks. So yes, it is to do with tension, but its definition is different. Now, tensile strength is to do with something called the maximum limit of something called stress, which can act within a body before it will break. So what we say is that if the amount of external stress is more than tensile strength, then instead of developing that much tension, the string or the rope or whatever will just break at that point. So that is to do with tensile strength. Yes, so Samarth, your conclusion is correct that out of the four fundamental forces known in nature, gravitational force and electromagnetic force are the ones that we see most commonly in our everyday life. Because in our everyday life, we don't experience what is happening inside an atom, or more importantly, what's happening inside a nucleus, or what's happening as the fundamental interaction between, subnuclear particles, like, quarks and all that. So we don't experience in our everyday life the weak and the strong forces. We only experience gravitational forces and electromagnetic forces. So we go through our entire life, unless we are involved in experimental particle physics, we are always experiencing in our daily lives only the combination of gravitational force and electric, and that too gravitational force only the Earth's gravitation. We do experience the moon's gravitation to an extent, like there are tidal waves created by the moon. Okay, then change seasons created because the gravitational pull of the sun is different at different positions of the Earth's orbit and all that. So a little bit of that is happening, but predominantly we experience the Earth's gravitational force on the surface of the Earth as human beings, and we experience all these types of electromagnetic forces. So yeah, in this case, the tension will balance the gravitational force. So here in this case, you will also note that the tension's magnitude will be equal to the weight of the object, because as you can see, this block, it is at rest. So forces are balancing. So it's at rest. So this upward tension acting on it has to balance its weight. So mg is equal to. So the heavier that block, the more the amount of tension that will be stretching that string. Okay, people. So with that, we conclude today's lecture. Yes, tug of war is a case of tension only. The more the amount of pulling force that each team applies, it creates more and more tension. If you pay close attention to it, you will realize that in tug of war, what is actually pulling the string? It is the frictional force. The frictional force between your hand surface and the string surface. The more strongly you're gripping the string and the more you're pulling it with your muscular force, the more amount of friction it is inducing. If your grip is weak, it doesn't matter how much you pull, your hand will slip. If your grip is very good, but your muscular force for pulling is not that strong, even then it will not create too much tension. You might grip the rope very heavily, but you're not pulling it too much. It won't create too much tension. Or you might pull it with a lot of force, but your grip is not strong, so it won't create enough friction. Yes, sometimes your hand gets cut in very deeply. That happens because of that friction that is actually causing your skin to get literally ripped a little bit because of that. because of the excessive frictional force. Just like if you rub your hand with a lot of force against a rock surface, it can cause blisters or it can cause the skin to cut. Again, that is friction. So again, at the molecular level, kya ho raha hai? It is electromagnetic interaction. And the molecules of the surface of your skin are interacting with the molecules of the surface of the rock or the rope you're pulling or whatever through electromagnetic interactions. So it's very interesting that all these everyday forces that we experience, at the fundamental level, what is responsible for them is the charge of electrons and protons. It's nothing else. It's the interaction between charged particles. Right, people. So with that, we bring to a conclusion today's lecture. Now, I would in this week's assignment for you guys, I will also suggest some reading. Okay, so that you understand and you are able to appreciate more about these things along with some problems. So if I will suggest some reading from Resnick Halliday as well as H.C. Verma as well as from the module. So whichever book is available or if some combination of books is available with you, please do that reading along with the problems also. Okay, I will resend the module on the group. I have sent it last week once you did. Okay. Yeah, Newton physics also you can study circuits. That's also a nice book. Okay. Right, so that's it, people. All the best and wish you the best.